understanding and use graphs of energy versus reaction coordinate during the rate determining step. Relate the change in temperature to reaction rates through the Arrhenius equation, and relate the change in activation energy to reaction rates. Okay, so we want to talk a little bit about transition state theory and kinetics. So this is what is happening during an elementary step. For a one-step reaction, there's a barrier to reaction. It needs a certain energy to be activated. So you could think of the transition state as all the possible ways that the molecule can get from one point to the next point. Most of these are just impossible to cover, but there's going to be one mountain pass, right? We're in Colorado, we know mountain passes. There's a mountain pass that gets you from one valley to the next valley with the least extra energy, and that's the transition state. And the energy usually comes from molecular collisions. So when it gets energy in just the right way, then it has enough energy to move over the mountain pass into the next valley. Again, it's going to be taking the lowest high energy route. It takes the mountain pass, not over the mountain peaks. So right, if you're going up to Loveland Pass and you see everybody skiing down there, that is where we're going. We're not going to go straight over the mountains. So, all right, so some information about the transition state. Again, that's the top of the mountain pass. It's the lowest high energy state, but it is high energy. You need energy to get there. It's very short-lived, right? Because once it gets up to the top, it just falls over into the next valley. Usually consists of things like partial bonds that are only partly formed, where the reactant bonds are partly removed and the product bonds are partly formed. So you see something like this. So in this case, we have a transition state intermediate between, you have bromine replacing the OH and ethanol. And at the end, you have methyl bromide. And in the middle, you've got this weird situation where it's bounded to both the oxygen and the bromine, but only partly. You get these weird molecular orbitals where the electrons are all over the place. It's pretty high energy, and so you got to get a lot of energy to get up into that. And so it's relatively rare that it happens, which is why these molecules are stable. You need to put it in the right circumstances that reaction can happen. So the transition state geometry looks something like this, where it's bonded to both of those. Usually it'd be in an sp3 state. Now it's in, I don't know what state, some sort of semi-sp2 where it's sharing a bond. And we didn't really talk about bonds like this because these are not stable bonds. These are higher energy bonds. They're the lowest high energy bonds you could form, but they're still higher energy bonds that are in between the reactant and the product. And this state right here is exactly the peak of that there. It's the least bad way to go between these two molecules. And so what we can do is we can look at the energy as a function of the reaction coordinate, the progress of the reaction. So here I've got the reaction coordinate. So at the beginning, when the reaction coordinate is 0, it's all the reactants, and when it's 1, it's all the products. And then in this direction, it's just the energy. So what we call this point here, the highest point, that's the transition state, sometimes called the activated complex. And the activation energy is the energy to go from the reactants up to the transition state. That's the amount of energy you need to get to that point. And then but the change in energy of the products, or enthalpy, if you're including pressure as well, that's actually going to be this difference. So you go from the reactants, you drop to get to products, but you have to go up to get the activation energy. So the activation energy, again, it's the transition state minus the reactants, whereas the energy of the reaction is just the energy of the products minus the energy of reactants. We've seen that a lot of times before. And it's important just to visualize what's going on. So what I'm essentially doing, this graph is essentially, put the graph diagonal there. This is the react. So over here is the beginning of the reaction coordinate. Over here is the end. And this curve over the transition state is the same as this curve here. We're just collapsing it down from 3 dimensions into a 1-dimensional graph. So that's what it just visualizing that mountain path, that this is essentially your progress along I-70 as you're going up Loveland, taking the bridge over Loveland Pass, right? That it's your progress along I-70. That is where you hit the middle of the tunnel and you're at the top. So that reaction diagram was for an exothermic reaction. Here we have a diagram for an endothermic reaction, right? The change in energy from reactants to products is positive. So in this case, our activation energy is large, going from reactants to products, and it's smaller going from products to reactants. So this has a smaller activation energy. It takes less energy to go from products to reactants, but it still takes energy to go from products to reactants. We have to get that initial barrier up before we slide down and gain some energy, you know, with its exothermic and reverse, right? Because in exothermic and endothermic reactions, you just flip them around, and exothermic, the reverse of an endothermic reaction is exothermic and vice versa. Okay. Again, but it's the same. We're essentially looking at the mountain pass from the other direction.